Very first thing we want to do is address functional groups. Okay, so there's a couple resources when it comes to functional groups. First and foremost, of course, in the slides, you've got this. Okay, this is the functional groups to keep in mind. These are the ones that I would highly encourage you to recognize right off the bat. So if you see any of these things in a structure, boom, you should be able to name the functional group. Okay, and we're going to introduce some differentiation in terminology that isn't in any of the slides or lectures, but we're going to try and differentiate it here within the class. So I want you to be able to look at a structure and name that functional group. Okay, so these are all functional groups that I think you are responsible for when it comes to an exam. When it comes to homework, when it comes to the specs quizzes, the world is your oyster. Sea? Ocean. It's big. You're responsible for everything, and I don't expect you to have them memorized, but I expect you to use the resources that you have at hand. Okay? To that end, the resources that you have at hand, officially your textbook, but I did also post this, which I did a little bit of digging online and stole this from somebody. It said something about Creative Commons, so I think it's okay. And what this does is very similar to what I did, but with a bunch of other colors. Okay? Drew in all quote unquote the functional groups in organic chemistry. So what you should be able to do is to look for a functional group depiction within this and name it. So you should be able to look at a structure and go, that's an amine. That's a carboxylic acid. That's a sulfone. Okay? Does that mean you're responsible for being able to do all that at will at any given point in the semester? No. Okay? For the quiz, yeah, and even on the specs quizzes, those are simple functional groups. It's going to be really hard for me to go through and weed out these ones are too complex, these ones are okay, because I don't know exactly what ones they're throwing in on the quiz. For people that have asked about it, what I'm doing is opening up your specs quiz and I'm looking at your 3 attempts. Right? And in some cases I looked at them and been like I get it, I know what you were trying to do, that's not at all what the question was asking, because you don't have the right breadth of what you would need within functional group labeling or naming to be able to address that. Right? So a little bit of clarity, hopefully through those emails back and forth to those students, or just looking at it and being like, nah, I think you're fine, and just giving you credit. Okay? Which I'll also point out, because I don't think everybody's aware of this. You want more attempts, you ask, that's fine. I open it up, I look at what you've submitted. In a couple cases, I've looked at what you've submitted and been like, nah, you're good, I'm not giving you another attempt, here's full points. I'm done with it. You've proved what you needed to do across the breadth of those 3 specs quizzes. I'm fine just accepting that you know it. Right? No one has then challenged me on that. You'd be like, well, I really don't know it. Give me another attempt. I mean, I would do it, but you've shown what you need to. That's fine. So if at any point you're like, this is just getting too overwhelming, send me the email, let me look, let me have that conversation to be able to make that decision. If you don't want to have that conversation, that's okay. Get what you get. Kind of make sense? Okay. To recognizing functional groups. So what should we be able to do? So look at the image. Okay, now that it's memorized, ta-da, structure. What functional groups are present? Okay. So we're now starting to pick up some patterns, and we're seeing some shout-outs behind these. Okay, so you said you had an arene, so we'll circle that as an arene. Okay, thank you. No, that wasn't the arene. What's the arene? The hexagon?
No, the double bonds.
Okay. So cool, the double bonds. Okay, so that's the arene. Sometimes referred to me as an aromatic. This is one of the reasons why I don't like nomenclature. Because one of the things that we push with nomenclature is there must be one name that rules the compound and everybody calls it by that. What's dihydrogen monoxide? That's water. Right out of the gate, the simplest frickin' molecule, and you're telling me there's a different name for it. Just imagine what happens when you pull up a compound like this. Okay? Trying to name that, we pull up Wikipedia. Wikipedia might actually have the name for it. No one in their right mind is going to call that by the actual name because it's awful. So what do they call it? Well, something that makes total logical sense. They call it Taxol. Where the hell did that come from? Because the other name sucked, so I invented a different one. Welcome to nomenclature. So what you're forced into within nomenclature is that you're supposed to know all these rules, how to name a compound, because it's supposed to be the universally accepted thing. It's not. It isn't, which is why it's dumb. Okay? It will be frustrating. I'm sorry, there isn't a whole lot I can do about that. Okay? It is something you're responsible for, but where you're responsible for it isn't what the hell is that structure's name? It's how do I name that? Right, and this is where I gotta be careful. Naming functional group, yes, it has an alcohol. Nomenclate it. The nomenclate is now going back to all of the rules that outline nomenclature. Now, I do care what the functional group is, which is why we have to name it, because naming the functional group now changes the nomenclate name that I'm going to come up with. And if you're wondering what nomenclate means, it's a word I made up to describe the action of providing the nomenclature, which is the name. Okay? Kind of make sense? Okay. So nomenclature is going to be vastly simpler molecules. Okay, vastly simpler. But I could give you a molecule like Taxol and say, name the functional groups. I'm not asking you to name the structure. I want you to be able to find the functional groups present within it. So how do we go through and do this? Okay, so we just circled one, right, up there, and we called it an arene, which I made as a comment to somebody in a message. So we got to backtrack out. Functional groups to keep in mind. So ta-da, in this list. Do we see that functional group in this list? Should we do a little back and forth? Picture in picture. I think I can do picture in picture, sort of. Sort of, kind of close enough? Does that work? I think the circle is over there. So now all we're going through and doing is matching what these functional groups are, what they're supposed to generally look like, to what we see in the picture. Okay? And that's where someone said arene, which is fantastic because the word arene is spelled A-R-E-N-E, which isn't in the list I told you to memorize. Why? Because nomenclature is not fucking universal. Okay? I call it aromatic. Does that mean it's just me? No, the world freaking does this. Okay? So it's trying to acknowledge what functional group is present. So when it comes to the functional group quiz, if you said there's an arene present, but it was keyed as aromatic, you are wrong.
I said incorrect.
Okay, that works.
Yeah.
And that's going to be insanely frustrating. That's when you send me that email, I need another attempt because I can't figure out what's going on. And I would look at it and be like, no, you're fine. You got them all right. That one you got wrong because you called it something that wasn't in the key. That's fine. Does that make sense? And that happens in a couple cases. Alkyl halides are also known as haloalkanes. How is it keyed? It's keyed one way because I found it for somebody else within the specs quiz. Okay? So those are things that I have to manually go through and check. It's easier for me to manually check when you all say, I need help. Okay, now I can go in and check you and see what's going on with it. Eventually, at some point, hopefully this semester, I'll be able to sit down and manually go through and check everybody's for every individual quiz. God, I can't believe I signed up for this. To verify that you're getting credit where credit was due. Does that make sense? I'm asking you to help me by complaining. We good? Okay, so back to Karina's question. What other functional groups are present? Anyone daring? Volunteer something? So I'm going to do it for you. Oh, carbon-oxygen double bond, therefore I have a ketone. Is that a ketone? Nope. Mother. Why is it not a ketone? Okay. When we're looking at the ketone, okay, this is going out to 2 carbons. If we look at the thing that I identified as a ketone up here, it's going out to a carbon and an oxygen. Why does that change the functional group? What? Why is changing the element change the name of the functional group? The properties of that element are changing the chemistry of the core functional group. Because the chemistry changes, the name for that functional group changes. This, back to that, I didn't need a pen anyway. Back to the functional group thing, that's where this comes into play. Right? Which, yeah, it looks really goofy and weird, but what this is trying to address is that when we talk about functional groups, I'm saying if I bond a hydrogen to a carbon, and in particular if I bond it through a sigma bond. Did we talk about hybridization yet in the lectures?
Yes.
Is that pushed on you? Yeah. Probably don't like it, tough. Okay? That's a sigma bond. Well, if I have a hydrogen bond into a carbon, I can define that as an alkyl. Okay? If that carbon is also singly bonded all the way around, I will call it an alkane. How do I know to call it an alkane? A couple things we could do. One, we go back to this. Carbon, singly bond, alkane. Does that make sense? Is that helping a little bit? Maybe.
In the video, you named one of them a methyl, and I was having trouble figuring out why it wasn't an alkyl.
So methyl is now starting to bring in IUPAC. Okay. Alkane is the broad class of carbons that are single bonds. So does a methyl is it a carbon with single bonds? Yes. That you could call an alkane. Yes. Okay. That's identifying the functional group. If I now want to nomenclate, I want to be more specific than just say, oh, it's alkanes. I want to say it's one carbon. I'm going to call it meth to represent one carbon. But I also said YL. Well, why did I say YL? YL suggests that that carbon is attached to something else that's more important than one carbon. The YL says it's a substituent. It's a thing hanging on something of a higher priority. Do we like that? No. Tough.
So on back to the drawing. So the aromatic that you circled, that functional group, the one below it, so would that be an amine? Or, because now it's an oxygen to a nitrogen. Well, have we gotten there yet? I mean,
So this one, again, the language is going to become nasty on this because you're trying to piece together all those different things. So I would slow it down because if you don't know the words,
yeah.
you use the words you do know. I have an oxygen double bonded to a carbon. Yes, okay, I do have that. Okay. Is that a functional group on its own? Okay. To answer that question, what we could do is we could go back to this thing and say, do I see just a carbon double bonded to an oxygen in any of these choices? No, because it's not a functional group on its own. Because depending on what I connect to that carbon, that changes the identity of the chemistry. And because the chemistry changes, the effing name changes. Right? So when we're looking at a carbon double bonded to an oxygen, it is actually technically identified. This is dealing in pi, because there's two bonds, right? We have a carbon bonded to an oxygen. It's a carbon, sorry,
Carbonyl, and then nitro.
carbonyl, because it just sounds weird to call it a carbonyl, really. Carbonyl. Okay? No, it says YL. Why? Because by definition, it has to be a substituent. Okay? But this is a loose term substituent. I need to be able to define what that functional group is by defining what's connected to that carbon. So as soon as I define what's connected to that carbon, I can now go through and identify the new functional group. Why does this matter? Well, let's use the example walked through in the lecture. I think walked through in the lecture. What functional group am I looking at? So we could go with a hydroxy. I heard somebody else say a different thing. Somebody over here. Okay, I heard someone say alcohol. OH isn't alcohol because if I attach, NH there is water, alcohol. That would make life really interesting. Okay? So no, water's not an alcohol. That's just an OH. That's a hydroxy. If I attach a carbon here, now maybe I could call this an alcohol. Alcohol is going to have a certain chemistry. But even with this, I'm now limited because what happens is I've got 3 potential sites that I could place something around that carbon. Okay? And if what I place at those sites doesn't affect the chemistry of the hydroxy, it's an alcohol. Okay? So it would be nice if I had a label that I could use for this thing doesn't affect the chemistry. R. That's the point of R. R is something that has no effect on the rest of what's shown. Typically, R is carbons or hydrogens, and that's it. Okay? But it could be other things. Okay? And so depending on the circumstance, unfortunately, R is going to fluctuate up to yin-yang. Was that a question that I needed to answer? Are you guys good? I'm going to say you're good. Okay? So that's an alcohol. Cool. We put an extra carbon on that. Yay, we have a good party. Whatever. What happens if I take 2 of those bonds that carbon was, and I bond them both to the same oxygen? Is this now still an alcohol? No, this changes to something else. Why does it change to something else? Well, what is that functional group called? It's called a carboxylic acid. Is that going to change how it interacts with my body? Yeah. Imagine drinking, yay, I'm drinking alcohol, woo, have a good time, drinking now and carboxylic acid, you just took a giant swig of vinegar. Is that a slightly different response? Yeah. That's a massive chemical change. Because that's a massive chemical change, I need to call that something else. I need to name it differently. So when we're looking at these functional groups, we're starting relatively simple, but then we have to be aware of what else connected to it. Why is this important? Back to Andrew's question. Because Andrew went through and called out the carbon double bonded to the oxygen. Okay? He used fancy words. Okay? And then said, but it's also bonded out to this. Okay? We should also technically include that carbon as well. Okay? The carbon up top is effectively an R group. That's not going to tweak the chemistry enough. How do you know that? Sucks to suck. You don't. You don't know that. Okay? That's going to come with more experience. Sorry, that's all I got. Okay? But that's going to qualify as an R group. That aromatic ring is not affecting the carbonyl enough to say I need to call it a new name. Okay? Well, how different do you need to be from somebody else to get called a new name? I don't know. Well, like everybody has a different name. That's not true. There's lots of Michael Hunts in the world. Google it. What the hell you Google that one? It's a fun little joke. Okay? In any case, we go back to our structure here and say, okay, well, that one's an R group. I don't really care. It's just carbon. This one's an N. N is electronegative. If N is electronegative, could that have an effect on this?
Yes.
Dang. Which means?
Different name.
It could, yeah, have a different name. How do I know it has a different name? Which is getting to Christina's question. How do I know it has a different name? No, how do I know that? How do I know that? How do I know it has a different name? You start looking at all your little pictures and being which of those pictures matches that picture. I heard some sighs as potentially like, oh, I get it now, but also potentially like, oh, that really sucks and that's painful. Okay? That's why I don't like giving you all of those. And I would argue we should sit and be happy with these. Okay? Are you going to see all of these ones? No. I could probably go through and start crossing some off. You won't see. Okay? Or you'll see them, but you won't name them that way. You won't worry about it. Thiocyanates. You've probably already dealt with thiocyanates, right? Where have you dealt with thiocyanate? Gen Chem nomenclature. That was an ion you had to deal with. Have you dealt with the S with 2 oxygens? Or 4 oxygens? Where's my 4 oxygens? It's not there. We can call it a sulfonate ester. You might also call it sulfuric acid. So when you change the identity of what those atoms are, that starts to change the name. Okay? The nomenclate name. Which is why being able to identify your function groups can be powerful. But do you think it's really important to be able to identify a sulfonate ester? Lecture 1. You're saying no. You said no last time, so I'm not sure that's fair. So she's the only one that watched the first frickin' lecture? Come on. Why are you saying to delete it off my periodic table? I don't have to worry about it. Okay? Is it something that could show up in the thingy, the specs quizzes? Yes, because it did. Not the sulfonate ester that I'm aware of, okay? But the sulfur bonded to 2 carbons did show up. Okay? Kind of, sort of? Okay. Next piece. Back to this. Ta-da! Is that a functional group that I just circled?
No. It's part of the overall function.
And see, this is an interesting one. And you may have made that little face. At least a couple people answering quiz questions effectively answered that they saw this functional group in a structure. And I understand why you're saying it. Because what do we see there? Okay, we see a methyl. That's a carbon bonded out to 4 different things. Okay, and if we, this is a lot of back and forth. This is killing me. We go back over to here. Do we have a carbon bonded to 4 different things? Go away, dictionary. Yeah, we call it an alkane. Oh, I got an alkane here. Why do we not care about alkanes? They're everywhere. I would bet every structure we look at this semester will have a carbon in it somewhere that is bonded to 4 other things so that we could call it an alkane. Why do we not care about alkanes? Ooh, this now gets more chemistry. This is cool. I like this. Why do we not care about alkanes? Why is looking at the carbon-hydrogen bond structure not relevant? But looking at the carbon or the oxygen-hydrogen bond is relevant. Go for it.
It's not reactive.
This is not reactive. This one is reactive. Why? Not.
Because CNH are stable.
Because CNH must clearly be a stable bond. If they're not reactive, they must be stable. But why are they stable?
Aren't the hydrogens just there to satisfy the top tab?
No. Hand wavy, you could make some kind of strange argument like that, but I'd say no. Why is the carbon-hydrogen bond not reactive? Push it further, yeah.
And it has
The carbon to hydrogen bond is a non-polar covalent bond, which means it generates 0 charge. And if it generates zero charge, is there any reason for it to talk to anybody else? Nope. Which means its interaction with the world is next to nothing. It's zero. And if it doesn't interact with the rest of the world, does it react? No. That's why alkanes are effectively irrelevant.
So would that be another case of the R being
So this could pass back to why we would typically reference R groups. Do we need to know that it's a methyl and not an ethyl? Well, what's methyl versus ethyl?
carbon chain?
The amount of carbons in it. Is that relevant? Yeah, because that's now changing parts of the structure. Okay? They may not do anything super important, okay, in and of themselves, but if you have more of them, that's going to change how that molecule interacts with the world. So we do need to now quantify that information for an individual molecule. Okay? Particularly something like Taxol. What's the deal with Taxol? It's an anti-cancer drug. Okay? As a drug, that's ingested by humans. If I change that methyl to an ethyl, that's going to change how it interacts with the world, which means it could change how it interacts in our body, which means it could take a very useful anti-cancer drug and turn it useless. That's kind of a big deal. I want to make sure it's useful. Or, worse,
Harmful.
it could actually make it harmful. Right? So depending on what you're looking at when you're looking at it, you will change the levels of specificity behind what you're trying to identify. Is that exciting? You're probably like, that's daunting. I don't know all the different situations that I have to be dealing with. You're right, you don't. But that's why we tend to start not looking at Taxol and start looking at relatively simple molecules. And we slowly build our way up to molecules like Taxol. We never really look at Taxol. Kind of, sort of? Okay. Christina, do you feel a little better about being able to identify your functional groups?
Kind of,
At least have a path?
yeah.
Okay. Which then pushes us back to the nomenclate. Okay. So to nomenclate, I want to now be able to look at a structure we're just going to hope for the best. I want to be able to look at a structure and actually associate a name with it, so that I can now theoretically name this, and then when I say that name to people, they convert the name in their brain, turn it into the structure, and we're now on the same wavelength. Does that ever happen? No, we draw a flipping structure, and I show you the structure, and we talk about it. Okay? But that's the point of nomenclature. It's what we're aiming for. Okay? So to go through and deal with the nomenclature, what do we need to do? Where do we start? Okay. The best place to start is to identify the longest carbon chain. Okay. So, where's the longest carbon chain?
Is that on that left side? Starting there?
The left side?
The other one? The other
Okay.
one.
I'm just going to be obnoxious and say, I'm going to start from the top. Have I identified the longest carbon? Oh, wow, that was aggressive. What's wrong with me?
Well, this one was in the lecture, so maybe I'm cheating, but the function group at the end is the highest priority one, so you need to include that.
All we're trying to do is identify the longest carbon chain, though. Is there a carbon out there? And that's what becomes fun, is we just got multiple answers. Several people in the class said, yep, there's absolutely a carbon out there, and several people said, nope, there's not. This is part of being able to recognize the drawings and all come to the same conclusion. That takes practice. There is absolutely a carbon out there. There's a point at where those lines meet that defines a carbon. So yes, there's a carbon. Okay? So now I've identified the longest carbon chain. But you, brilliant you, said I was wrong and that it should have been this way. Right? Who's right? Me or her? Both of us come to the exact same conclusion. It doesn't change or alter the name, so it doesn't matter which one we use. Okay? So cool. I've identified my longest carbon chain. What's my next step?
Identifying functional groups.
No. No. This is a little gray area, because some of what you're saying would be okay. No.
Numbers?
Take a half step back from numbering.
Identify the carbon chain's name.
Yes. Count the carbons in your chain. I don't care about numbering necessarily yet. I want to know how many carbons I have to deal with. So I could go through, and you're right. Wouldn't it be easy? Like I go 1, 2, 3, 4. You're right. You could go through and do that, and that could get dangerous. Okay. So this is where I would go 1, 2, 3, 4, 5. And for those of you at home can't tell, I'm tapping the screen at each of those points. Okay. So I already forgot the number. 5. 5 carbons have been identified in that chain. Okay? Because I know I have 5 carbons in that chain, I now know some information about my name, my nomenclate. What do I know? I know I'm looking at a pent. Okay? So I've got a pent. The next part of my name actually boils down into kind of 2 pieces, because both pieces will show up within the name. Okay? There's a piece that I would call the hybridization, which is really looking at the backbone of those carbons and being like, what's the hybridization? This one addresses a little bit of gray area behind it. Right? What we're largely doing is ignoring any larger functional groups. Right? So if I look at that top carbon, if this thing turns for me, okay, what's the hybridization of that carbon?
SP3.
SP3. And I would know that because
There's implied hydrogens.
there's how many implied hydrogens?
3.
3 implied hydrogens, and then one, I'm drifting, and then this one, which would mean there's 4 bonds around it. 4 bonds, or 4 groups of electrons, is sp3 hybridized. Okay? Next one. Also sp3. So some people, again, how are you jumping to that? Because the people that are saying sp3 didn't draw out a bunch of hydrogens. You're doing it in your head. You've started to process some of that content. That content that even freaking 2 days ago, you're like, oh, the world's going to crash down and end. You're already processing that in your head. Okay? And if you're not there yet, that's okay. You're just a half step behind some of the other people in the class. That half step will come right with you real fast. Don't stress. Okay? How about the next one?
SP3, SP3, and then SP2.
That one switches to sp2. Okay? Again, don't stress a whole lot about it. How is that going to affect our name? Well, that one that turned sp2 is looking at a higher priority functional group. It's a higher priority functional group because it's connected out to those oxygens. So I'm going to ignore that one for my hybridization effect, which means when I look at the backbone behind this, the hybridization for all of these was sp3. The hybridization name, our nomenclate for sp3, okay, we're just going to put a dash in here. It's not an official dash. Ain, okay? And if that was all we had, there was no other high priority functional groups, we drop an E in there and close out the name. That would be the end cap. However, do we have a higher priority functional group? Yes. Okay. Which means I'm going to have to put something else in there. So now what I've got to do is acknowledge my high priority. Okay. How do I know the priorities of my functional groups? Yeah. Someone said the answer and everybody's going to be unhappy with it. You have to memorize it. Okay, why? Because it's nomenclature. Nomenclature is strictly memorization. Anybody that tells you different is lying, and they don't know what they're talking about. Nomenclature is 100% memorization. What you're trying to do is memorize the rules that some long-dead dude came up with and said was the be-all, end-all to all nomenclature. And they were wrong. Okay? But that's what you're being asked to do. Okay? So there are higher priority functional groups in here. Okay? Now we could push to that question, well, what are the higher priority functional groups? This now gets into the naming aspect, not nomenclature, naming, because you have to be able to identify and name the functional groups that are present. So what functional groups do you see?
Acid.
Okay. An acid, I'm okay with you calling it acid. I would prefer you called it a carboxylic acid, which I know is obnoxious. Is that it? Is that the only high priority functional group there is in there?
Nitrogen. Down there.
We have a nitrogen. Is a functional group called nitrogen. It's an amine.
Oh, yeah.
Okay. How do I identify that that's a carboxylic acid and an amine? Rewind 10 minutes. That was our conversation about looking at the structures and what the functional groups are supposed to represent to be able to name the functional group. Once you've identified the name of those functional groups, you now have the ability to nomenclate. Okay? To nomenclate, we now have to go back through and decide, because we have two high priority functional groups, which one is the highest priority. Okay? How do we decide which one's the highest priority? You memorized it off the nomenclature slide that says carboxylic acids is at the top. Yeah. Okay. And how do we name carboxylic acids? Okay. It says oic acid. Okay. That O can be a little bit weird depending on the system. Okay. Do we call it pentanoic acid or do we call it pentanic acid? Which one sounds better? Pentanic? Sounds like a death metal band. Or pentanoic? The answer is with the O. In this case, we want the O. Okay, so we've got pentanoic acid. We do have a potential issue popping up here, though. We have a high priority functional group. Part of the naming system is naming our structure and then naming where all of the pieces are located. Did I say where the acid was located?
Not yet.
No, I haven't, which means officially I should go through and name where it is located. Okay? This goes back to the naming or the numbering system. Right? So I now have to number my chain in such a way that I give the highest priority functional group the lowest possible number. Which means when we had initially counted it, where we're like, oh, it's 1, 2, 3, 4, 5, right? Was entirely backwards. And so the numbering system would be wrong. And so we would want to number from 1, 2, 3, 4, 5.
So to give the highest priority functional group the lowest number, we should always start our carbon chain counting from the highest priority.
So awesome question. Okay, awesome question. And let me provide the counterexample to it. So for the sake of the recording, should you always start your numbering from the carbon where your highest priority functional group is located? No, that's not going to work. Why? What's your longest carbon chain? 5. If you started your numbering where the highest priority functional group was, the nitrogen, you don't have a 5 carbon chain anymore. You have a 4. Okay, does that make sense? The numbering we've outlined is correct. Okay, because it puts the amine at the lowest number depending on our numbering system. Does that make sense? Okay. And just with that question, hopefully it starts to address there's rules upon rules upon rules upon rules. Okay? There are tons. So what I want you to be able to do is to pick up some of the pieces behind how we process this. I'm not strictly concerned that you get the name, but do you recognize the pieces and some of the things that are necessary to go into it? Okay? And there's parts that, yes, you're responsible for. Okay? That slide that, at least, Tyler? Can I steal your iPad? Thank you. Which I would put up, I'll put up on the slides later, but that thing, right, vaguely rings a bell. The reds and the blues and the numbers and that's clearly all my circling, right, because it looks sloppy. Tyler's got better handwriting than I do, right? So that slide, everything on that slide, I would highly encourage you to memorize because that covers the nuts and bolts of nomenclature. And everything else starts to become nuances and what happens if this, if this, if this, right? So, where did the acid show up? At position 1. Where should I write the position 1?
Do you really have to?
Okay. It's such a benign question, right? And there's 3 fucking answers to that question. The first answer is IUPAC. The full, formal, correct way to do it is you put the 1, your locator, as close as humanly possible to the whatever you're referencing. As close as possible is right here. Whoop, that's an eraser. Is right there. So this isn't the words that you understood before. This is pentan 1-oic acid. I have to add the 1 into it? That makes it sound stupid. I don't care. That's what IUPAC says. But you get a vast majority of people being like, that sounds stupid. I'm not doing it. I'm putting it out here. Because the 1 can't possibly refer to the pent, because that's the freaking chain. It can't possibly refer to the ane, because they're all single bonds all the way through. The only thing that 1 can apply to is the oic acid. So you know what, IUPAC? Shove it. You're like, dude, people can say no to things. Look at yourself. Look at what I've asked you to do. You've said no to me more times than you can probably count already. Okay? But what happens to students? You're now responsible for everybody's screw-ups. Welcome to the party. Last one, okay, which I believe Andrew was saying. Where does the acid have to fall? As a hint, there's only 2 answers. The acid has to be at only 2 spots, ever. The beginning or the end. And if it was at the end, this wouldn't say oic acid, it would say dioic acid. I had to have 2. Because the first one would always be, by definition, at position 1. Okay? Which means, do I really need to specify the 1? No, I don't. So I could also just delete that. You enjoying nomenclature yet? Good. Maybe you'll stop asking me questions about it. Okay, you're still responsible for it. Okay, so cool. Do we have the name yet? Oh my God, 20 minutes later. No, what are we missing? Okay, what other group? Ah, cool. So what you did was you didn't just say, well, you circled the amine, we haven't labeled the amine yet. You also acknowledged that at this point, now that we have the parent name, we have to now name everything else as a substituent in front of our main name, which means we should identify all of our substituents. So we also have this thing in orange, and we have our amine. Okay? The thing in orange. What is the thing in orange? Slower. And don't go, math. It's 1 carbon. If it's get it, slower. 1 carbon, we call that 1 carbon meth. Because it is a substituent on the main chain, we add the YL. Okay? What was the NH2? An amine. Okay? But the amine gets tricky, and this is where Tyler has a cheat for us. Okay? Because the amine is a high priority functional group, which means it could alter the ending of our name. Except because the acid was there, the amine doesn't go at the end, it has to now get shifted to the front. And because it's shifted to the front, it can potentially change its name. Okay? And when we look at that slide, I only am sort of positive. Okay. When it's at the end, we call it an amine. Okay? When it's not the highest priority functional group, the slide says arrow, turn it to something else. And we turn it to amino. So this is an amino. Okay? Dash, dash. So the dash is trying to signify where the rest of the main chain comes in. So now what do we do?
You specify the areas in which they are in the carbon chain.
Said another way as locate.
Yeah.
Locate where those things are. Because we've already numbered, where's the amino? Where's the methyl?
Or we alphabetically set.
Now we've got all of our glorious pieces, but we still don't have a name, because what do we have to do? We have to put all those pieces together to come to a final glorified name. Okay? In that final amalgamation, is there a correct way to put the substituents? Yes, of course there is. And so if you call it 4-methyl, 2-amino, pentan 1-oic acid, you're wrong. Even though with that name you would have drawn this structure. You're wrong. Because the rule says we organize the substituents by alphabet, and A comes before M. So this stupid thing is 2-amino 4-methyl pentan 1-oic acid. Cool. Also known as biologist in the house. Threonine. It's an amino acid. I could be wrong. I think I got it. Okay. Why do biologists not call it 2-amino 4-methyl pentan 1-oic acid? Because it's fucking stupid to call it that, and they invented a different name to call it because it makes it easier to reference the name. That's what it comes down to. Okay. How much of this are you responsible for? I would argue black box, I don't want you writing it out, but if you did everything down here and I gave you 4 multiple choice answers, would you be able to assemble it? Yeah? Done. Agreed. That's how we function. So what I want you to be able to do is to identify all of those pieces. With all of those pieces in hand, now look at your multiple choice and be like, oh, that one says it's bute. It's not bute, it's pent. Delete. Wrong answer. That one says it's an amine. It's not an amine, it's an amino. Delete. Wrong answer. Okay? That's how I want you to be able to reason through it. Because ultimately, you're never going to use nomenclature, ever, 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 ever. And I'm happy to go on record in a recording being very vehemently angry at anybody that forces people to do nomenclature, because they are stupid, quite literally, and I accept all repercussions.
I have a question about a smart word question.
You're trying to get me to stop talking about nomenclature?
Well, no, it's about it.
Oh,
It said that for the priority, that the ether and alkyl are the same priority.
Yes.
Is that, in your list it said that the methyls are
I hope nobody had any questions about what was wrong up there, because I just deleted it.
higher.
We're good with that? Okay, cool. Nomenclature. You, twit, come back here. So, a couple things are going on here. If you took a screenshot, did you take a screenshot? Yeah.
But alcohol, oh,
Does your screenshot show those numbers?
mine says 8, 9, 10.
Yeah. Because somebody hates nomenclature and eventually realized the numbering system I put in was incorrect. All 3 of those are tied. So I updated the slides. I can't update the lecture because, well, I can update the lecture, but the lecture, I need to re-record that whole process. Does that make sense? Okay. Because yes, those ties are obnoxious, and there's technically one that's not on here that Cardi, your textbook covers. He throws in nitros as a functional group as well. It's also similarly tied with those. So if you're going to pull questions from the textbook, you'll see nitros as a potential substituent. And I'll draw that up for a second. And those are equally paired with alkanes, ethers, and halides. Actually, I'm curious. Oh, let's just make this big. That did not do what I wanted it to do. You're going to give me nitro? Yeah, there it is. Ta-da, nitro. Okay. So if you see NO2 show up, NO2, they're referencing a nitro. As a functional group, it acts the same as an alkyl, ether, or halide. Should we add that to our list? You'll only see it if you do practice within Cardi. I don't put it on exams. Question, Katie? Am I getting your name right? Jake. Close enough. Let's address your answer without pulling it up. Next question. Can we do something that's not nomenclature? Oh, you have a question about nomenclature. Okay, give it to me.
I already erased it, but I was gonna ask for the E and Z, the cis and trans for that one that you pulled up.
I feel a little bit better about that one. E and Z is not horrible. Okay. Actually, no, we got some legit content on this one. Okay. Remember early in the semester, I asked about, on the board, so it's not in a lecture recording, I asked about those two structures versus these two structures, right? Okay. And I asked if they were the same or different in each of those cases. Okay. And what the class poll said, when me just kind of eyeballing what everybody was suggesting, is that you said these two structures were different and these two structures were different. And I kicked back and said, what did I say? You guys remember? The first two were the same. And the next two, we're going to call right different, but I'm going to put it in some really big, these are big, big air quotes, because it is technically not different. It's, you wait like another week. Okay? Language sucks. Why are the first two the same? And because you had the hybridization lecture, you should now be able to answer that question.
They'll have the sigma bonds, which are able to freely rotate.
Cool. So when we look at those two structures, the only difference is that I took that bond and I rotated the methyl group down. All I did was a rotation. Okay? And because that bond is a sigma bond, okay, I can rotate it. Why can I rotate sigma bonds?
Because they're not tied.
A sigma bond is where I'm taking my two caps. Sigma bond is a direct overlap of orbitals, which means that little thing with the pen demonstration overlaps the hole on this one, and I have a sigma bond. What happens when I rotate the pen? Sorry. They're still connected. The overlap of the orbitals stays constant, which means for a sigma bond, I can freely rotate that. Cool. What types of orbitals am I using to make a sigma bond? S-type orbitals. Okay? So those S-type maintain constant overlap. That's why we call it sigma, because we're using S-type. What are S-type orbitals?
SP hybridized.
SP is an example of an S-type.
SP2.
SP2,
SP3.
SP3,
S.
S. There's 4 types. Any of those 3 orbitals are going to make S-type bonds. Okay? So we'll call those sigma. What happens when we move over to our other drawing? Well, we still have that sigma. And again, remember, this is entirely arbitrary. The other one's a pi. So to make it look like the bottom one, I would have to do that same thing. I would have to take this and rotate about that bond to bring it down to look like this. Yeah? Everybody on board? Right. Sigma. What happens with the sigma? Freely rotate, not a problem. What's different from a pi versus a sigma?
They're stuck on an axis, or
A pi can move without changing, like,
What orbitals make a sigma bond? S-type orbitals. What orbitals make a pi bond? P orbitals. Okay, our p orbitals have a different shape. That different shape is that dumbbell, right? Up and down. Okay? So if we're looking at, and this is so not going to work, but we're going to try it anyway. Summoning. Scaring off vampires right now. Just get you a shield. Okay? So we're talking about these 2 orbitals coming together, the black and the red, in my normal fingers, right? Boom. Sigma bond is made. Did the p orbitals overlap?
Yeah, they're both alive.
Did they overlap? Ah, interesting. Because when we look at it end on or side on, no way in hell they don't overlap, but change your viewpoint. All the pictures change. Does that kind of make sense? Kind of get the feel of that? Okay. For those people being, but the orbitals still don't directly overlap in space. You see it? Is that better? Can you see the purple pen? Lies. You can see the purple pen? Okay, thank you. Okay, why not? Because the red pen overlapped it. Okay, but you might be, but that's a different overlap. It absolutely is a different overlap because the blue pen. Can you toss me a blue pen? The red and the black pen directly overlap, whereas our now blue and purple pen don't directly overlap. Okay, so it's a different type of overlap. And you might say, well, the whole point of overlap is that what happens? Electrons can move. So through the black and the red, the electrons are jumping back and forth super easy. But the purple and the blue, there's this giant white space in between where they aren't overlapping. So when we look at that side-on view, we don't see them overlapping. So we say, well, then the electrons can't jump, right? But if you remember back in Gen Chem 151, when we talked about electrons, they're really, really tiny, and they have this nasty little ability, okay, that is often portrayed in the movies as quantum, okay? And if we dig into the quantum chemistry, what we end up finding out is that an electron can tunnel, okay? So it can move through a space, and this is the kicker, without being in the space. Yeah, that's why they say quantum for all the movies, because they just be like, no one else can explain it, so we can just make up whatever we want. It works. Okay? Which means an electron on my purple can make it to my blue. So it can jump. It can be shared. Can it now? Okay? And for people being like, I'm not positive, can it now? No. When can it? When they're close enough in distance that it can make that tunneling. Guess what that distance happens to match? The sigma bond. So once that sigma bond has been made, we're now in a distance where those p orbitals, the electrons in the p orbital, can tunnel over to the other one, as long as there's another orbital there. What happens if we rotate?
It breaks.
Is it overlapped anymore? The overlap broke. And if the overlap is broken, can it tunnel? No. And if it can't tunnel, there's no bond. Whoa. So what does that mean? If we look at a pi structure in that upper right-hand corner, that molecule with the pi bond cannot rotate the pi bond. Because if it breaks, or if it tries to rotate the pi bond, I no longer have a pi bond. That's a different structure. So the only way to get between these two structures on the right is to break a pi bond. And when we're talking about same and different, what we're talking about is how can they freely move? Okay? That's why the ones on the left are allowed to freely move, because it's a sigma bond connection. That connection is allowed to freely rotate, because each of those rotations don't change the orbital overlap. Pi bonds, they do. Okay? So, if that's the case, if I look at the same structures over here, if I went through to name these, I could name the top one. Sorry, let me rephrase that. You can name the top one blank. Thank you. And if you're wondering, like, wow, how do you come up with that fast? A little bit of practice. 4 carbons in a line, they're all single bonds, so but is the prefix, ane was our suffix for all single bonds. Butane. What's the bottom one? Butane, which makes sense because it's the same molecule. Okay? So it should have the same name. Okay? So that's all fine and dandy. So let's get rid of that one because that one's boring. What's going on over here? What do I name these? Okay, cool. We get bute. They aren't all single bonds all through it, so I got to be a little bit more specific. What's the hybridization now in that backbone? It's sp2. The sp2 hybridization gets called ene. Do I have another high priority functional group? Nope, so I can drop the E and I get butene. Have I now named this compound? No, why not? Not you two.
Okay.
Because you gave me the butenenes. Why is this not the name of the compound?
Where the double bond group.
Where's the double bond? Is it at position 1, 2, 3, 4? I gotta define it. Okay? Where we define it is we start our numbering that gives us the lowest number. Okay, again, for where that substituent first shows up. Okay, in this case, it doesn't matter which direction we number it, and we'll number it from where it first appears. So our numbering is going to continue through the double bond, so 2, 3. Okay, so I would call this 2-butene. Next one. Try it again. What is the name for the next molecule? Okay. And maybe we're getting some hesitation because you're like, it's the same name. And why is that a problem if it's the same name? They were different molecules. So we need to add something to our nomenclature system that allows us to identify that that double bond has a very particular configuration in one case versus the other. Okay? There's a couple different ways we can go through and do this. We're going to do it on the bottom one. Yeah. First, cut the double bond in half perpendicular to the bond angle. So that's our first step. Now what we want to do is look at each of those halves. Okay? And I want to look at the atoms connected to the carbon of the double bond. What atoms are connected to that carbon? Okay. Only on that half. It's only connected to a hydrogen? I don't see any hydrogens. I don't understand what you're saying.
The carbon in the.
Carbon, awesome. There's a carbon here. Okay, so I care about that carbon, okay, for the sake of the recording. I want to know what, up here, that guy, how many carbons are connected to it, or what things are connected to it on this side of the line. That's why we cut it in half. So it is connected to a carbon. Is that all it's connected to? There's an implied hydrogen. Where should I draw that implied hydrogen? Should I draw it like here?
Sure, try it.
And why are you saying no? Because it's the way you asked the question, Mike. You're giving me hints. Yeah, I'm giving you hints. Okay, I saw another one, another hand gesture. Should I draw it here?
No.
Should it be like more trigonal?
When we go through and do our drawings, we want to try to mimic the real world as much as humanly possible. These are two-dimensional drawings that we're trying to mimic and use as representations of the real world. Okay? If our drawings suck, so will our interpretations. Okay? This is why some people don't like abstract art. That sounds like I'm saying abstract art sucks. That's not what I meant to say, for the record. So there's an implied hydrogen. And I should draw it in a way that replicates as much as possible that 120-degree bond angle, because that carbon at the center has 3 groups of electrons. 3 groups of electrons correlates to a trigonal planar bond geometry. Okay, so cool. Now I've identified the atoms connection. Now what do I do? Which of those atoms is a higher priority? What defines priority?
First, the electronegativity.
No.
Well, then the bond is.
What defines priority? Number of atoms connected. That's not a bad idea. No. Where is it in my list? Hydrogen's not on the list, so that's immediately I'm going to say no. You mean there's another list I have to worry about? Yes. But it's a list you've already worked with. Atomic mass. Not molecule mass, atomic mass. So when I'm going through and comparing these two, the atomic mass of this carbon is, shouldn't have been that much a struggle. We got a periodic table. We look at the periodic table, and the atomic mass of carbon is 12.01. The atomic mass of hydrogen is 1, so carbon gets the higher priority. Do I factor in these other hydrogens?
If you were competing against two
Okay.
carbons?
The only reason I factor in the next atom is if there's a tie. You mean there can be a tie? Yes, there can be a tie. There's always a tie. Okay? What if there's a tie to forever? Then you can't establish priority. And if you can't establish priority, it didn't matter if it rotated. You would never be able to tell.
Like the other, like the one we were showing, it didn't matter which carbon we started on in that, amino that we did.
We didn't have an alkene there. This structure, there's a tie between this carbon and this carbon. I can't tell a difference between them. So if I redrew this, did I rotate the bond? I don't know. There's no evidence that would allow me to determine if that bond was even rotated. That's why I would ignore this naming system for it, because there's no evidence. This naming system on our right, with our black structures, yeah, there's evidence. We can see that. Kind of make sense? Okay, so now what do?
For the other side?
Rinse and repeat, other side. Which is higher priority, carbon or hydrogen? Carbon, because?
Heavier.
Higher atomic mass. I don't know why I don't like the word heavier. Okay, now what do? Cut parallel. Where are the stars? They're on the same side. Because they are on the same side, I now have a differentiation. If we go up and did that for the top one, let's kind of delete some of that extra stuff that's up there. What we would end up finding is we would get a star, and when we cut that one parallel, they are on opposite sides. Okay? So now we have to come up with a nomenclature system to identify same or opposite. Do we want to write same side? No, we need a new system to be able to label this. Okay? And unfortunately, we come up with two naming systems. Okay? We get cis, meaning they're on the same side, and we also get Z. Okay? For the top one, we would get trans or E. Cis and trans describe where any two things are relative to each other. Okay? So if they're on the same side or opposite side. It says nothing about the identity of what those things are. Okay? So I could reference the hydrogens and say the hydrogens in this bottom one are cis to each other. Do I care about hydrogens when I go in and look at my name? No. So calling this cis-butene or cis-2-butene technically isn't correct because I'm not using a proper nomenclature system. So cis and trans are really these kind of relative terms. Z and E, for lack of a better word, we could call it absolute, or we could call it IUPAC. So if I want to now define this for this bottom one, and this can get fun, what could I go through and call it? Well, I could call it 2Z, my 2 looks like trash. 2, I don't think it's getting any better. Z, butene. I could call it 2Z, that's a Z, but-2-ene, right? Because where does the 2 got to go? It's close to where the functional group is humanly possible. Okay, I could call it 2Z, 2-butene. You mean I can do pretty much any permutation of all? Yes. Welcome to nomenclature. Okay. This example is so simple that typically what you would get people doing is this. Okay? Officially, you pull out that extra information to the front of the name, and then you run your name normal.
So the top one be 2 butane?
So the top one would then become 2E-butene. Okay? Anybody notice a pattern with the dashes? Because we've been doing lots of nomenclature. When do we use a dash?
Like a number or like a single letter.
Between numbers and letters, right? That's when we use a dash. Do you see a dash between the 2 and the E? Or the 2 and the Z? No. Okay? So typically the dash shows up between numbers and letters. It doesn't show up when we're looking at E and Z, or you'll see R and S next week, 2 weeks. 2 weeks. Let's go. Let's hope for 2 weeks.
This will be, do you just put a front, a slash if there's cis and trans on something instead of a dash? Like,
Can I delete everything? Okay. So in answer to your question, we'll drop orange. So if I had a structure that had multiple double bonds, okay, I would have to specify E and Z for each of the double bonds that needed it. Remember, not all double bonds need it. Okay? So I could go through and say there was a Z double bond, there was an E double bond, what the hell, there was another E double bond. Okay? That's telling me the orientation of those double bonds, but I now need to know where those double bonds appeared for 8.
you comma.
Mike. And you would drop commas in between. Does that make sense?
Yeah.
And again, we didn't address it yet, but it's going to come down the road. Okay, you could also see 3R. The number placement is going to be awful. 9S. So you could see something that addresses all of those kind of detail. Okay, which then, to me, right away begs the next question. Which one of those should come first? Z, E, R, or S? I don't know. That's why I don't ask a question that's that complex. Or I make it multiple choice and they're all the same. Okay? Make sense?
Yes.
Okay. We're not done with nomenclature forever for the rest of the semester. You're not going to ask another question about it. Somebody's got a nomenclature question, don't you? I can see it. What's the next question? Really? You don't have any other questions?
You're saying, sometimes it doesn't matter to like the years and specify the it doesn't matter. Or
So let me clarify that. And so in that statement, I believe what you're chiming in on is this crap fest that's going on down there. Okay, on where we specify, how we specify, all those gory details. Does it matter? 100% it does. IUPAC says this is the way you do it any other way, you're wrong. Okay, would I ever ask a question that says which of these is correct? No. So does it matter for you? No, don't worry about it. Don't stress. You're going to be looking at multiple choice, whichever one gives you the proper pieces. You got it. Just 2 more hours, guys. Come on. You got it. More questions.
I don't know if everyone's here on the slides, but like anti-bonding, I'm like kind of stumped on anti-bonding.
You're asking like that. Okay. Simplest story. We'll try and make it simpler with p orbitals, I think. When I draw p orbitals, right, when we're talking about anti-bonding, what we're talking about is bringing 2 orbitals near each other in talking about what kind of interaction can happen out of them. So number one, we're talking about atom A, that's this atom, and atom B. Okay. Did I draw a proper p orbital?
Yeah. P. Oh, no. Oh.
Why no? A p orbital. Did I draw a proper p orbital?
Is it Z? Are Z's ever used?
I don't give a which axis. Did I draw a proper p orbital? So you can start to be, well, your artistic qualities are inappropriate, Mike. You need to, I don't care. Did I draw a proper p orbital?
Yeah.
No. Okay. And what comes out of this is how electrons move. How do electrons move? In waves. Because there's in waves, you have amplitudes. You have the crest of the wave, and you have the trough of the wave. The crest of the wave we call positive, and the troughs are negative. When we look at a p orbital, it has those two things associated with it. We don't see it for an s orbital because the s orbital is uniform. What we see for a p orbital is right here, known as a node. That node is where we're transitioning from positive to negative. Okay? If you got to go, you're welcome to go. I'm going to try and do this as fast as I can. I apologize. Blame Andrew. Thank you, Andrew. Okay? So now what we're talking about is what are the possible ways these two atoms could collide with these p orbitals. So we're bringing this atom in this way, this atom in this way, so that those p orbitals overlap. Okay? Well, we're going to get two possible ways that these could interact. Okay, right? Where they're overlapping there? Everybody see that? Okay, we could get that, and then, just for giggles, we'll show it higher. I have no idea why my shape is falling way out of whack, but it is. Okay, and we get the overlap there. So there's two possible ways we can do it. I'm just drawing to random little spaces. Okay? What are those two possible ways? Well, the first one could have come in positive and negative, right? And we'll just maintain that one. The other one could have come in where it aligned negative and positive, right? Okay. What happens with the other interaction? Positive, negative, and then positive, negative. Right? So we aren't flipping both. We're only flipping one. These are the only two possible combinations that we can get. Why is this important to us? Okay. Well, if I take two troughs and I bring them near each other and they overlap, what happens to the size of the trough?
It expands or gets bigger.
It gets bigger. It gets more intense. We get a deeper trough. Okay, this would be two waves in constructive overlap. Okay, so what this ultimately means for us is that little shaded area is going to change a little bit. Okay, because I'm going to expand the area that I would expect electrons to exist. So what's going to end up happening is I'm going to see something more along these lines. Where they overlapped, I expect more electron density because it's getting a larger amplitude. What's happening on the outsides? Well, they aren't really interacting, so relatively, they get smaller. Okay? What happens in the top scenario? I'm taking that negative, and I'm overlapping it with a positive.
They cancel out. Or
Yeah, perfectly right. They cancel out. So what happens in that space is I don't get any electrons. Okay? So I would see a little bit in here, I'd see the little bit over there, and I'd see a little bit in here, and I'd see a little bit over there. Okay? And what becomes important comes back to this thing, node. The node is where our electrons don't exist. This is the transition point between our peak and our trough. So when we overlap two of them, what happens? Two nodes. What happens in the top one? Three nodes. Okay? Why does this become important to us? The next thing, these are now the possible ways these orbitals can overlap, period. This is what happens. These are the molecular orbitals. Okay? This middle system, our molecular orbital, fudge me, that just says molecular orbitals, deal with it. Okay? This is like 1s, 2s, 3s, 4s. They exist. You can't delete these. This is an orbital. Okay? remember, the center of each of these p orbitals was the nucleus coming in. In this bottom case, what did I do with electrons?
You shared greater bond.
Sort of. I increased the probability of finding the electrons between atoms. And if I have electrons between atoms, we might call that a bond. Okay, so that's where you're jumping to that bond. It's an increased probability of finding electrons there, so that's a bond. Okay, so we could call that a bonding. Bonding starts with B. What happens with the top one? What happened to the amount of electrons between the atoms?
You severed, I guess, what would be the right?
Did I increase the probability of finding electrons there or decreased it?
Decrease.
I decreased the probability of finding electrons between the atoms. Okay? This interaction still exists. It doesn't disappear. It's there. It's an orbital. Okay? But what is happening within it? And this is where people go, oh, that's not a bond. That's not true. Okay? These two atoms are not bonding. These atoms are now bonding, and that bonding situation creates two orbitals. So I can't call that top one not a bond, because it is still a bonding orbital. So I can't call it not a bond, but I don't want to call it a bond. Why do I not want to call it a bond?
Because you have bond.
What does a bond mean to me?
Increased bond.
Increased probability of finding electrons. I have decreased probability of finding electrons in that space. So I need a new name. I need a new name that helps me to recognize that this isn't a bond, but it's also not a bond. I think I got that right.
So anti-bond, or anti-bond.
This would be defined or described as an anti-bond. We could also change the conjugation language and call it anti-bonding orbitals. Okay? That, at a minimum, is what we're talking about when we talk about bonding and anti-bonding. What I picked was a very simple case looking at the p orbitals, but ultimately what this happens is every interaction you get between atoms generates a bond and an antibond. Every single one. Right? How do you know you actually have a bond in the molecule? That's a much harder question. To have a bond, what must be present? Electrons. Have we defined anything about electrons? No. Since we haven't specified anything about electrons, we can't define if there is a bond or not. All we can say is that we have a bonding orbital and an anti-bonding orbital. The identity of whether there's a bond or not, okay, is irrelevant. Kind of, sort of?
Yeah.
We're way past time. I need to stop.